Hello there, and welcome back. Tonight we're going to travel somewhere most minds never venture, not forward into the stars or backward to the dinosaurs, but deeper still, to a time so ancient that even the shape of the continents would be unrecognizable. We're going to a world locked in ice. Not just the poles, not just the mountain tops, but the entire planet, frozen from one horizon to the other, oceans and all. Imagine standing at what is now the equator, the warmest part of the Earth, and seeing nothing but glaciers stretching endlessly in every direction. The sky above is pale and silent, washed of colour by the cold. The air is so cold it burns your lungs with every breath, and beneath your feet, beneath layers of ice that reach down more than a kilometre, the ocean lies trapped in darkness, cut off from the sun, slowly turning strange and hostile. The water there is twice as salty as today's ocean, so cold it should be frozen solid but remains liquid only because of its extreme chemistry. This is Snowball Earth. It sounds like something from myth or imagination, a fairy tale of ice and silence, but it happened, perhaps more than once. Scientists have spent decades piecing together the evidence, and what they've found challenges everything we assume about our planet's stability. The Earth, it turns out, is capable of extremes we struggle to comprehend. The same planet that supports tropical rainforests and coral reefs has also been a frozen wasteland, white and silent from pole to pole, for millions of years at a stretch. And tonight, as you settle in wherever you are in the world, we're going to explore this frozen chapter together. We'll ask how such a catastrophe could happen, how life somehow survived it, and whether the conditions that caused it might ever return. Because the most unsettling thing about Snowball Earth isn't that it happened so long ago. It's that the forces that triggered it, the delicate balance between atmosphere and ice, carbon and sunlight, are still at work right now, even as you listen. Before we begin, I'd love to know where you're joining from tonight. Is it late where you are? Is the world outside quiet? Or is there still the hum of the day fading into evening? Whatever time it is, whatever sky hangs above you, we're about to step into a world where time moved slowly and the cold was patient. If this kind of journey appeals to you, if you enjoy drifting through big questions at a gentle pace, I'd be grateful if you tapped like or considered subscribing. It helps others find this space, and it keeps these quiet explorations alive. Now let's begin. Let's walk backward through the ages, past everything familiar, past recorded history and the rise of civilizations, past the extinction of the dinosaurs and the first stirrings of complex life. Let's go to the frozen heart of our planet's strangest chapter, where the oceans turned to ice and the fate of all future life hung in a cold, silent balance. The story of Snowball Earth didn't begin in the ice. It began in the rocks. For centuries, geologists had noticed something strange about certain ancient formations scattered across the globe. In places as far apart as Australia, Namibia, Canada, and China, there were thick layers of glacial debris, the kind of material that only forms when glaciers grind across the land, picking up boulders and sand and dropping them in jumbled piles. This wasn't unusual on its own. The Earth has experienced ice ages before, and glacial deposits are well understood. What puzzled scientists was where these particular deposits were found. When they examined the rocks more closely, using a technique called paleomagnetism, which measures the orientation of magnetic minerals at the time the rocks formed, they discovered something troubling. These glacial layers hadn't been laid down near the poles where ice belongs. They had formed near the equator. That finding made no sense. The tropics are the warmest part of the planet. Even during the most severe ice ages of recent history, glaciers never came close to equatorial regions. Yet here was evidence that, sometime in the deep past, ice had reached latitudes that should have been warm. The discovery sat uneasily in the scientific community for years. Some researchers suggested the evidence was wrong, that the magnetic readings had been altered over time, or that the rocks had somehow shifted position through tectonic movement. But as more sites were examined across different continents, the pattern held. Glacial deposits from roughly the same age, all showing signs of low-latitude formation. Something extraordinary had happened. The scientific detective work that followed ranks among the great achievements of geology. Researchers fanned out across the globe, collecting samples from cryogenian rocks wherever they could be found. They measured chemical compositions, analysed isotope ratios, dated volcanic ash layers, and painstakingly reconstructed the positions of the ancient continents. piece by piece the evidence accumulated. Not only had glaciers reached the equator, but they had done so on multiple continents simultaneously. The glaciation wasn't a local phenomenon or a regional quirk. It was global. The entire planet had frozen over, or very nearly so, in a way that had no parallel in later Earth history. This realization transformed our understanding of climate. Before Snowball Earth was recognized, most scientists assumed that the climate system had built-in stabilizers that would prevent extreme states from developing. The ice albedo feedback was known and understood, but it was thought that other processes would kick in before ice could spread to the tropics. Snowball Earth proved that this assumption was wrong. Under the right conditions, the climate could tip into a state from which there was no easy return. The planet's thermostat, usually so reliable, could fail. In 1992, a geophysicist named Joseph Kirschvink proposed an explanation that would eventually reshape our understanding of Earth's climate history. He called it Snowball Earth. His idea was simple but radical. What if, during certain periods in the distant past, the Earth's climate had spiraled into an extreme state, one where ice didn't stop at the poles but kept spreading until it covered the entire planet? It sounded impossible. Ice is highly reflective. Once it starts to spread, it bounces more sunlight back into space, which cools the planet further, which allows more ice to form. This is called the ice albedo feedback, and it's well understood. But most scientists assumed there was a natural limit to how far ice could spread. Surely something would stop it before it reached the tropics. Kirschvink argued otherwise. If certain conditions aligned, if atmospheric carbon dioxide dropped low enough, and temperatures fell past a critical threshold, the ice albedo feedback could become unstoppable. The planet would tip into a frozen state from which escape seemed nearly impossible. He called this state Snowball Earth, and from a vantage point in space, that's exactly what it would have looked like, a giant white sphere reflecting most of the sun's energy back into the void. His hypothesis was met with skepticism at first, but over the following decades, as more evidence accumulated, as geochemists and paleontologists added their own findings to the puzzle, the idea gained traction. Today, most scientists agree that at least 2, and possibly more, global or near-global glaciations occurred during a period called the Cryogenian, between roughly 720 and 635 million years ago. These weren't ordinary ice ages. They were something far more extreme, events that pushed life to the brink and reshaped the trajectory of evolution for all time. To understand how the Earth could freeze so completely, we first need to set the stage. The world of 700 million years ago was nothing like the one we know today. The continents hadn't yet assembled into familiar shapes. There was no Atlantic Ocean, no Himalayan range, no recognizable outline of Africa or the Americas. Instead, the land masses were clustered together in a supercontinent called Rodinia, centered roughly near the equator. Picture a single vast body of land surrounded by an immense global ocean, a world where the geography itself was alien. The atmosphere too was different. Oxygen levels were lower than they are now. The ozone layer was thinner. Life was still almost entirely confined to the sea, and most of it was simple single-celled organisms. There were no animals, no plants on land, no forests or grasslands. The continents were barren rock, shaped only by wind and water. And yet, even in this strange world, the same forces that govern climate today were at work. The sun warmed the planet, clouds formed and rain fell, carbon dioxide moved. Between the atmosphere, the oceans and the rocks in a cycle that had been operating for billions of years. It was this cycle, or rather a disruption in it, that would bring the cold. Rodinia had begun to break apart. As the supercontinent rifted and drifted, new coastlines formed, exposing fresh rock to the elements. Rain fell on these young surfaces, and as it did, it triggered a chemical process called silicate weathering. This is a slow reaction in which rainwater, slightly acidified by carbon dioxide from the atmosphere, dissolves certain minerals in the rock. The dissolved carbon is eventually carried to the ocean, where it combines with calcium and other elements to form carbite sediments. Over millions of years, this process removes carbon dioxide from the air and locks it away in stone. Normally, silicate weathering is balanced by volcanic activity, which releases new carbon dioxide into the atmosphere. The two processes form a kind of thermostat, keeping Earth's climate relatively stable over geological timescales. But something went wrong. Around 720 million years ago, the rate of carbon dioxide removal began to outpace the rate of volcanic release. Scientists now believe this imbalance was caused by a combination of factors. The breakup of Rodinia exposed vast areas of volcanic rock called flood basalts to weathering. At the same time, volcanic activity at mid-ocean ridges dropped to historically low levels, reducing the supply of new carbon dioxide. The result was a slow but relentless decline in atmospheric greenhouse gases. As carbon dioxide levels fell, the planet cooled. Snow and ice began to spread from the poles. At first, the changes were gradual, but as the ice advanced, it began to reflect more and more sunlight. The Earth's albedo increased, temperatures dropped further, and with each passing century, the feedback loop grew stronger. Eventually, the ice reached a critical latitude somewhere around 25 to 30 degrees from the equator. At that point, models suggest the feedback became unstoppable. The planet tipped into a new state, one where ice spread all the way to the tropics, covering the oceans and locking the world in a frozen shell. This was the beginning of Snowball Earth. The ice albedo feedback is one of the most powerful and dangerous mechanisms in Earth's climate system. It works because ice and snow are extremely reflective. Fresh snow can bounce back more than 80% of the sunlight that strikes it, compared to just 6 or 7% for open ocean water. When ice covers more of the Earth's surface, more solar energy is reflected back into space, which cools the planet, which allows more ice to form. It's a classic positive feedback loop, one that amplifies any initial cooling. Under normal conditions, this feedback is kept in check by other factors. Warmer ocean currents carry heat toward the poles, clouds and water vapor trap some of the outgoing energy, and the carbon cycle works to restore balance, adjusting greenhouse gas levels over millions of years. But during the onset of Snowball Earth, these stabilizing forces weren't enough. The drop in carbon dioxide was too steep, and the cooling too rapid. As ice crept toward the equator, it passed what scientists call a bifurcation point, a threshold beyond which the system can't recover on its own. Once ice covered the tropics, there was no warm ocean left to moderate the climate. The entire planet became a giant mirror, reflecting most of the sun's energy and keeping itself locked in cold. Mathematical models suggest that once this tipping point was crossed, global temperatures plummeted. Average surface temperatures may have dropped to -40 or even -50 degrees Celsius. The oceans froze over, not just at the surface but potentially down to depths of a kilometre or more. Glaciers flowed outward from the continents, spreading across the frozen seas. The hydrological cycle nearly shut down. With no open water to evaporate, precipitation became rare. The atmosphere grew dry and still. It was in many ways a world in suspended animation. Some scientists have questioned whether the Earth ever reached a true hard snowball state, where every inch of the surface was covered in ice. Alternative models suggest there may have been thin patches of open water near the equator, kept liquid by geothermal heat or by currents beneath the ice. This slush ball hypothesis, as it's sometimes called, offers a slightly less extreme picture. But even in this scenario, the planet was almost entirely frozen. The question of whether it was a full snowball or a partial slush ball remains a subject of active debate. What's not in dispute is that the glaciation was global in scope and lasted for millions of years. The Sturtian glaciation, the first of the Cryogenian ice ages, may have endured for 57 million years or more. That's not a typo. 57 million years of ice. To put that in perspective, the entire age of dinosaurs, from the first theropods to the final extinction, lasted about 165 million years. The Sturtian glaciation alone covered more than a third of that span. For all that time, the Earth remained locked in its frozen state, the sun rising and setting over endless white, the ocean sealed beneath thick ice, and life, what little there was, clinging to the edge of survival. Beneath the ice, the ocean became a strange and hostile place. Cut off from the atmosphere, sealed away from sunlight, the waters turned dark and still. Without photosynthesis, oxygen levels in the water plummeted. The ocean became anoxic, a term that means devoid of free oxygen. In this darkness, iron began to accumulate. Under normal conditions, iron released by underwater volcanic vents reacts quickly with dissolved oxygen and precipitates out of the water. But without oxygen, the iron stayed in solution, building up in the deep ocean until concentrations reached levels not seen since the early days of the planet. This iron-rich water left behind a distinctive geological signature. When the ice finally melted and oxygen returned to the oceans, the dissolved iron reacted rapidly, forming thick layers of iron-rich sediment known as banded iron formations. These formations are one of the key pieces of evidence for Snowball Earth. They had disappeared from the geological record more than 1 billion years earlier during the Great Oxidation Event, when rising oxygen levels cleared the oceans of dissolved iron. Their sudden reappearance in the Cryogenian tells us that something extraordinary had happened to reset the ocean's chemistry. Life in this frozen ocean faced almost unimaginable challenges. Photosynthetic organisms, which depend on sunlight, could not survive beneath a kilometre of ice. The food web, such as it was, collapsed. Whatever organisms remained had to find alternative sources of energy. Some may have clustered near hydrothermal vents on the ocean floor, where volcanic heat and chemical energy provided a fragile lifeline. Others may have survived in pockets of meltwater, near the edges of ice sheets, where thin ice or cracks in the surface allowed traces of light to penetrate. Recent research has suggested that even during the deepest freeze, the oceans were not entirely lifeless. Chemical signatures in ancient sediments indicate that some photosynthesis continued, probably in limited areas where ice was thin enough to transmit light. There may also have been refugia, small patches of open water or warmer conditions where complex life could persist. But these were isolated oases in a vast frozen desert. The broader ocean was dark, cold, and largely devoid of the oxygen that most modern organisms need to survive. The temperature of the water itself was extreme. Recent studies using iron isotope ratios and snowball-era sediments suggest that brine pools in the deep ocean may have reached temperatures as low as -15 degrees Celsius. These weren't ordinary seawater conditions. The high salinity of the synglacial ocean, caused by the removal of so much fresh water into ice, allowed the water to remain liquid at temperatures far below the normal freezing point. It was a briny, frigid, lightless realm, as alien as any world in our solar system, and yet life survived. This is perhaps the most remarkable part of the Snowball Earth story. Despite conditions that should have been lethal to almost everything, the lineage of life on Earth was not broken. Somewhere, somehow, organisms held on. And when the ice finally melted, they were still there, ready to resume their slow evolutionary journey. The question of how life survived Snowball Earth has occupied scientists for decades. Several hypotheses have been proposed, each offering a different picture of where and how organisms might have found refuge. One possibility is that hydrothermal vents on the ocean floor provided the necessary conditions. These deep-sea environments are powered by geothermal energy, not sunlight. They host ecosystems today that thrive in complete darkness, feeding on chemical energy released by volcanic activity. During Snowball Earth, such vents may have served as lifeboats for microbial life, preserving the spark of biology while the rest of the planet froze. Another possibility is that meltwater ponds on the surface of ice sheets offered habitable environments. In modern Antarctica, small pools of liquid water form on and around ice shelves during warmer months. These pools are colonized by cyanobacteria and other microorganisms, which build layered mats on the pond floors. Recent research has found evidence of similar environments from the Cryogenian, suggesting that even on a frozen planet, pockets of sunlit water may have existed. These meltwater ponds could have been oases for photosynthetic life, allowing eukaryotes, the complex cells that would eventually give rise to animals and plants, to survive and even diversify. A third hypothesis focuses on the margins of ice sheets, where subglacial meltwater could have carried oxygen and nutrients into the ocean. Ice sheets aren't static. They flow under their own weight, and at the base of these glaciers, friction and pressure can generate enough heat to melt ice. This meltwater, rich in dissolved oxygen from contact with air at the glacier's surface, could have created localized zones of habitability where it entered the ocean. These glacier marine oxygen oases, as some researchers call them, may have been critical refugia for aerobic life. The latest research, published just this year, has strengthened the case for meltwater refugia. Scientists studying modern Antarctic ice shelves have found diverse communities of eukaryotes living in small ponds atop the ice. These organisms, which include algae and other complex cells, are remarkably similar to the kinds of life that existed before and after Snowball Earth. The findings suggest that above-ice environments may have played a key role in the survival and evolution of early complex life. Whatever the exact combination of refugia, the outcome is clear. Life made it through. The fossil record before and after the Cryogenian shows continuity in the kinds of organisms present. Sponges, which may have evolved before the glaciations, are found in sediments from both periods. Microbial life persisted throughout. The great extinction that might have been expected from such an extreme event never fully materialized. Life, it seems, is extraordinarily resilient. The Sturtian glaciation, named after the Sturt Gorge in South Australia, where evidence was first identified, represents the longest and most severe ice age in the geological record since the much earlier Huronian glaciation over 2 billion years ago. Understanding its duration and intensity has been a major focus of research. The glaciation appears to have begun suddenly, at least in geological terms, with ice sheets advancing across continents within perhaps 1 million years. Once established, the frozen state persisted with remarkable stability, maintained by the same ice albedo feedback that had triggered it. During these long millions of years, the planet was not entirely static. Ice sheets flowed under their own weight, grinding rock and depositing sediments. Volcanic eruptions continued, releasing carbon dioxide into the atmosphere. Hydrothermal vents on the ocean floor kept pumping minerals into the water. And somewhere, in Refugia, we are only beginning to understand life persisted. The geological record from the Sturtian period is fragmentary, as one might expect from a time when most of the planet was covered in ice. But what we have tells a story of extreme conditions. Thick deposits of glacial debris, called diamictites, are found on every continent, evidence of ice sheets grinding their way across the land, banded iron, formations, those distinctive striped rocks that speak of an anoxic ocean, reappear in the record after a billion-year absence. And everywhere, the same pattern, glacial deposits giving way abruptly to cap carbonates, the signature of a greenhouse-driven thaw. The end of the Sturtian glaciation was as dramatic as its onset. After 57 million years of ice, the planet warmed rapidly, driven by the accumulated greenhouse gases that had been building in the atmosphere. The ice retreated, the ocean mixed, and for a time, conditions stabilized. But this interglacial period was brief by geological standards, lasting perhaps 10 to 20 million years. And then the ice returned. The Marinoan glaciation, named after the Adelaide suburb of Marino where Australian geologist Douglas Mawson first studied the deposits, was shorter than the Sturtian but equally global in scope. It lasted from roughly 640 to 635 million years ago, a span of perhaps 5 to 15 million years. The mechanisms that triggered it were likely similar to those that caused the Sturtian, involving a decline in atmospheric carbon dioxide and the inexorable advance of the ice albedo feedback. But there are differences between the two glaciations that scientists are still working to understand. The Marinoan glaciation left behind somewhat different geological signatures. The banded iron formations that characterize the Sturtian are largely absent from Marinoan deposits, suggesting that ocean chemistry may have been different. The cap carbonates atop Marinoan glacial deposits contain unusual features, including strange tubular structures and barite crystals that speak of unique chemical conditions during the thaw. And the recovery from the Marinoan appears to have been even more abrupt than from the Sturtian, with some estimates suggesting the ice melted in less than 1 million years. One intriguing possibility is that the Marinoan glaciation was ended by massive volcanic activity. Researchers have identified volcanic deposits dating to roughly 635 million years ago in multiple locations around the world. If these volcanoes erupted during the glaciation, they could have accelerated the buildup of atmospheric carbon dioxide, hastening the thaw. Some scientists have suggested that the release of pressure as ice sheets melted may have actually triggered volcanic eruptions, creating a feedback that shortened the Marinoan compared to the Sturtian. This idea remains speculative, but it highlights the complex interplay between geology, climate, and the solid Earth during these extraordinary events. The Gasquias glaciation, the youngest and least understood of the Cryogenian ice ages, occurred around 580 million years ago. Unlike the Sturtian and Marinoan, the Gasquias appears to have been much shorter, lasting perhaps only 1 million years or less. There is also less evidence that it was truly global in scope. Glacial deposits from this period are found in some locations but not others, suggesting that while ice sheets may have expanded, they may not have reached the tropics. Some researchers classify the Gasquias as a severe regional glaciation rather than a true snowball event. The Gasquias occurred during the Ediacaran period, after the main Cryogenian ice ages but before the Cambrian explosion. Its relationship to the evolution of complex life is unclear. Some scientists have suggested that the Gaskias may have contributed to the extinction of certain Ediacaran organisms, helping to clear the way for the Cambrian fauna. Others argue that the Gaskias was too brief and too limited in extent to have had major biological effects. The question remains open, a reminder that even events we think we understand can hold surprises. The Sturtian glaciation, the first of the Cryogenian ice ages, eventually came to an end, but the respite was brief, after perhaps 10 to 20 million years of relative warmth, a period during which the planet began to recover and life began to spread once more. The ice returned. This second freeze, known as the Marinoan glaciation, was shorter but still intense. It lasted roughly 5 to 15 million years and may have been even more severe in some ways than the Sturtian. Why did the planet freeze again so soon after thawing? The answer likely lies in the same factors that caused the first glaciation. Silicate weathering continued to draw down carbon dioxide. Volcanic outgassing remained subdued, and the conditions that had allowed the first snowball to form were still in place. Once the planet cooled below a certain threshold, the ice albedo feedback took over once more, and the world plunged back into frozen darkness. The Marinoan glaciation left its own distinct geological signature. Like the Sturtian, it deposited glacial sediments at low latitudes across multiple continents. But it also left behind chemical markers that tell us something about the severity of the freeze and the conditions of its end. The most important of these markers are the cap carbonates, thick layers of limestone and dolostone that sit directly on top of the glacial deposits, with no transitional layers in between. These carbonates couldn't have formed during the glaciation itself. They required warm, shallow water, conditions that didn't exist while the oceans were frozen. Their sudden appearance, often in layers meters thick, tells us that the end of Snowball Earth was abrupt, a rapid transition from ice to warmth that transformed the planet in geological terms overnight. Scientists believe that the same mechanism that caused Snowball Earth also provided the means of escape. During the glaciation, volcanoes continued to erupt, releasing carbon dioxide into the atmosphere. Under normal conditions, this carbon would be absorbed by weathering reactions and dissolved into the ocean. But with the continents locked under ice and the oceans sealed beneath frozen surfaces, these sinks were largely shut down. Carbon dioxide accumulated in the atmosphere, building up over millions of years. Eventually, atmospheric carbon dioxide reached levels hundreds of times higher than today, perhaps as much as 350 times the current concentration. At that point, the greenhouse effect became powerful enough to overcome the reflective barrier of the ice. Temperatures began to rise, the ice started to melt, and once melting began, the process accelerated rapidly. Dark water replaced bright ice, absorbing more solar energy, raising temperatures further, melting more ice. The feedback that had caused the freeze now ran in reverse, driving a runaway thaw. The transition from snowball to greenhouse was one of the most dramatic climate shifts in Earth's history. As the ice retreated, the planet entered a brief period of extreme warmth. Global temperatures may have soared to 30 degrees Celsius or higher. The hydrological cycle, dormant for millions of years, roared back to life. Intense rainfall scoured the newly exposed land, washing enormous quantities of minerals into the ocean. This chemical deluge had profound effects. The ocean, which had been acidified by dissolved carbon dioxide during the glaciation, now received a massive influx of alkalinity from the weathered rocks. The result was rapid precipitation of carbonate minerals, laying down the thick cap carbonate layers that now serve as markers of the glacial termination. These carbonates formed quickly, perhaps in as little as a few thousand years, a blink of an eye in geological time. The cap carbonates are some of the most distinctive rocks in the geological record. They appear on every continent that preserves cryogenian sediments, sitting atop glacial deposits like punctuation marks at the end of a sentence. Their chemistry tells us that the conditions during their formation were unlike anything before or since. High temperatures, high carbon dioxide, intense weathering, and an ocean undergoing rapid chemical transformation. For life, the transition was both an opportunity and a challenge. The organisms that had survived the glaciation now found themselves in a radically altered world. Oxygen levels in the ocean began to rise as the ice melted and the water mixed with the atmosphere. Nutrients that had been locked away in the frozen seas were suddenly available. The ocean stratified, with warm, fresh meltwater floating atop colder, saltier water below. In this strange new environment, life began to diversify. The immediate aftermath of Snowball Earth set the stage for one of the most important evolutionary transitions in the history of life. In the tens of millions of years following the Marinoan glaciation, during the period known as the Ediacaran, the first large complex organisms appeared in the fossil record. These were the Ediacaran biota, a bizarre assemblage of creatures unlike anything alive today. Some resembled fronds or quilted mattresses, others looked like discs or bags filled with mud. They were soft-bodied, mostly immobile, and their relationship to modern animals remains a subject of debate. But they were undeniably complex, far more so than anything that had come before. The connection between Snowball Earth and the rise of complex life is one of the most intriguing questions in paleontology. Did the extreme conditions of the glaciations somehow trigger or accelerate the evolution of multicellular animals? Or was it simply a coincidence that the first animals appeared shortly after the ice ages ended? Several mechanisms have been proposed. One idea is that the dramatic environmental changes, the swings from frozen darkness to tropical warmth, created evolutionary pressure that favoured adaptability and complexity. Organisms that could respond to changing conditions, that could move, sense their environment and cooperate with others, would have had an advantage. Another hypothesis focuses on oxygen. The cryogenian glaciations may have helped oxygenate the deep ocean, either through the mixing of meltwater or through the shutdown of organic matter consumption during the frozen periods. Higher oxygen levels would have allowed larger, more metabolically active organisms to evolve. Animals, with their high energy demands, may simply not have been possible until enough oxygen was available. A third idea is that the mass extinction at the end of the Ediacaran, when many of the strange early organisms disappeared, cleared the way for a new wave of evolution. The Cambrian explosion, which followed shortly after, saw the rapid appearance of most major animal groups in a burst of diversification that continues to puzzle scientists. Some researchers believe that the environmental upheavals of the Cryogenian and Ediacaran set the stage for this explosion, providing both the ecological opportunity and the genetic toolkit for animal evolution. Whatever the exact mechanism, the timing is suggestive. For more than 3 billion years, life on Earth had been dominated by single-celled organisms. Complex multicellular life, when it finally appeared, did so in the geological aftermath of Snowball Earth. It's hard to believe this was purely coincidental. The extreme conditions of the glaciations and the dramatic recovery that followed may have been the crucible in which complex life was forged. Given what we now know about Snowball Earth, it's natural to ask whether such an event could happen again. The conditions that triggered the cryogenian glaciations, a drop in atmospheric carbon dioxide, a susceptible configuration of continents, a weakened volcanic output are all possible in principle. The ice albedo feedback that drove the runaway freezing is still a fundamental part of Earth's climate system. Could the planet tip back into a snowball state? The short answer is that it's extremely unlikely, at least on any timescale, relevant to human civilization. The modern Earth is very different from the world of 700 million years ago. Atmospheric carbon dioxide levels are currently many times higher than they were before the cryogenian glaciations, thanks in part to human emissions. This means the greenhouse effect is strong, keeping global temperatures well above the threshold needed to trigger runaway cooling. Even if carbon dioxide levels dropped dramatically, which would take millions of years under natural conditions, other factors would work against a new snowball. The sun is brighter now than it was in the Neoproterozoic, providing more energy to warm the planet. The configuration of the continents has changed, with land masses spread across a range of latitudes rather than clustered near the equator, and the biosphere is far more developed, with forests, grasslands, and ocean ecosystems that absorb and release carbon in ways that tend to stabilize climate. But the story of Snowball Earth carries a warning nonetheless. It reminds us that Earth's climate is not as stable as it might seem. The same feedback mechanisms that lock the planet in ice can also drive rapid warming. The same tipping points that caused the cryogenian glaciations could, in principle, trigger other kinds of catastrophic change. We live in a thin band of conditions that supports complex life, and that band can shift. Scientists studying Snowball Earth have drawn connections to modern climate research. The ice albedo feedback is already contributing to Arctic warming as melting sea ice exposes dark ocean water that absorbs more heat. The loss of ice in the Arctic and Antarctic is accelerating, and the effects are being felt around the world. While we're not heading toward a new ice age, the underlying physics is the same. Positive feedbacks can amplify small changes into large ones, and once certain thresholds are crossed, the system can shift into a new state that's difficult to reverse. The scientific debate over Snowball Earth is far from settled. While most researchers agree that the cryogenian glaciations were global or near global in extent, the details remain contentious. Was the Earth ever completely frozen, a hard snowball with no open water anywhere? Or was it more of a slush ball, with thin ice or patches of open ocean in the tropics? The distinction matters because it affects our understanding of how life survived and how the planet eventually escaped the freeze. Proponents of the hard snowball hypothesis point to the geological evidence: glacial deposits at equatorial latitudes, banded iron formations that require an anoxic ocean, and the absence of sedimentary features that would indicate significant open water. They also cite climate models that show how the ice albedo feedback, once triggered, should drive the planet all the way to complete ice cover. Under these models, any open water would quickly freeze over, and the only way out is through a massive build-up of volcanic carbon dioxide. Supporters of the slush ball hypothesis, on the other hand, argue that the evidence isn't quite so clear-cut. Some sediments from the cryogenian show signs of wave action, and other features that require liquid water. Certain organisms that depend on photosynthesis appear to have survived the glaciations, which would be difficult or impossible if all light was blocked by thick ice. And some climate models suggest that ocean circulation could prevent complete freezing, especially near the equator. Recent research from NASA's Goddard Institute for Space Studies has added nuance to the debate. Using sophisticated climate models that incorporate ocean dynamics, researchers have found that the Earth's natural circulation patterns can resist complete freezing, even under very cold conditions. In their simulations, areas of open water persist in the tropics, kept liquid by ocean currents that transport heat from lower latitudes. This slush ball state, while still extremely cold, would have been more hospitable to life than a true hard snowball. The debate continues, and it's likely that both sides contain elements of truth. Different glaciations may have had different characteristics. The Sturtian, which lasted longer, may have been more severe than the Marinoan. Regional variations in ice thickness and ocean circulation could have created a patchwork of conditions, with some areas frozen solid and others maintaining thin ice or open water. The full picture is probably more complex than any single model can capture. As we come to the end of this journey, it's worth pausing to consider what Snowball Earth teaches us about our planet and our place on it. The Earth, it turns out, is capable of extremes. It can freeze from pole to pole, locking itself in ice for tens of millions of years. It can also thaw rapidly, swinging from frozen wasteland to tropical greenhouse in geological instants. These transitions are driven by forces that operate on timescales far beyond human experience, but they remind us that the stability we take for granted is not permanent. Life, too, has lessons to teach. The organisms that survived Snowball Earth did so against incredible odds. Sealed beneath ice, deprived of sunlight, living in water that was frigid and devoid of oxygen, they found ways to persist. They clustered around volcanic vents, huddled in meltwater pools, clung to the margins of ice sheets. And when the ice finally melted, they were still there, ready to inherit a changed world. Their resilience is humbling. It suggests that life, once established, is remarkably difficult to extinguish. Even the most extreme conditions Earth can produce were not enough to wipe the slate clean. The thread of life, thin as it was, never broke. And from that thread, everything we see around us today, every forest and ocean and creature, eventually descended. There's also a deeper reflection to be found in this story. Snowball Earth happened long before humans existed, long before any animal with eyes or a brain could have witnessed it. The ice advanced and retreated in silence, noticed by no one. The struggles of early life, the near extinction and slow recovery, all of it occurred without consciousness to record or remember it. We know about it only because the rocks preserved traces, because minerals aligned with magnetic fields, because chemistry left signatures that patient scientists learned to read. In that sense, Snowball Earth is a reminder of how much has happened on this planet without us. The Earth is ancient beyond easy comprehension. Its history is written in languages we're still learning to decipher. And every time we uncover a new chapter, we're reminded that the present moment, however solid it feels, is just the latest page in a very long story. And so, as you lie here tonight, wherever you are in the world, consider the ground beneath you. That ground was once frozen solid or covered by tropical seas or part of a continent that no longer exists. The atoms in your body were forged in stars, cycled through oceans and rocks, breathed by creatures that vanished hundreds of millions of years ago. You're connected to all of it, to the ice ages and the thaws, to the first cells that learned to use sunlight and the first animals that crawled in the mud. The story of Snowball Earth is part of your story, whether you knew it before tonight or not. The cold has passed, at least for now. The sun rises each morning on a planet of liquid oceans and green lands. Glaciers still exist at the poles and on high mountains, but they are remnants, not rulers. The ice albedo feedback that once threatened to freeze the world is kept in check by a thick atmosphere of greenhouse gases, by the warmth of a brighter sun, by the steady circulation of ocean currents that carry heat from the tropics toward the poles. But the forces that cause Snowball Earth are still at work. The carbon cycle continues, moving carbon between air and rock and sea. The Earth's orbit still wobbles, volcanoes still erupt, and somewhere in the deep future, hundreds of millions of years from now, conditions might align again. The ice might begin to spread, the feedback might engage, and the planet might once more turn white. We won't be here to see it. Human civilization, even if it survives and thrives, will be something unimaginable by then, transformed by time and evolution into forms we can't predict. But the Earth will continue, and its long story will add new chapters, as it always has. Snowball Earth is not the end of the story. It's a reminder that the story is always continuing, always changing, always deeper and stranger than we expect. Let us now turn our attention to the ocean itself, that vast body of water that lay beneath the ice for all those millions of years. Because while we've spoken of the ice and the atmosphere, the carbon cycle and the feedbacks, the ocean was where the drama truly unfolded. It was in those dark waters that life clung to existence. It was in those depths that the chemistry of the planet was transformed. And it was from those depths that the conditions for complex life eventually emerged. The ocean during Snowball Earth was unlike anything we know today. Sealed beneath a shell of ice that may have been a kilometre thick or more in places, the water was cut off from the atmosphere. No oxygen could dissolve into it from the air. No sunlight could penetrate to drive photosynthesis. The entire global ocean became a single dark chamber, isolated and still. Under these conditions, the chemistry of the water began to change. Normally, the ocean is oxygenated by two processes. Photosynthetic organisms, primarily cyanobacteria and algae, produce oxygen as a byproduct of converting sunlight into energy. And oxygen from the atmosphere dissolves into surface waters, mixing downward through currents and convection. Both of these processes were shut down during Snowball Earth. Without sunlight, photosynthesis ceased. Without open water, atmospheric exchange stopped. The oxygen that had been dissolved in the ocean was gradually consumed by organisms and chemical reactions, and it was not replaced. The result was an anoxic ocean, a vast body of water devoid of free oxygen. This was not unprecedented in Earth's history. Before the Great Oxidation Event, roughly 2.4 billion years ago, the ocean had been anoxic as a default state. But that was before oxygen-producing life had transformed the planet. By the time of Snowball Earth, the ocean had been oxygenated for over 1 billion years. The return to anoxia was a dramatic reversal, a throwback to conditions that had not existed since the earliest days of complex chemistry. In anoxic water, iron behaves differently than it does in oxygenated conditions. Iron released by hydrothermal vents on the ocean floor normally oxidized quickly and precipitated out as rust-coloured sediments instead remained dissolved. It accumulated in the water, reaching concentrations that would be impossible in today's oxygen-rich seas. This iron-laden water was a signature of the Snowball Ocean, and it left behind distinctive geological evidence. When the ice finally melted and oxygen returned to the water, the dissolved iron reacted explosively with the incoming oxygen, precipitating out in vast quantities. The result was the formation of banded iron formations, layered sediments of iron oxide alternating with silica-rich rock. These formations are some of the most striking geological features associated with Snowball Earth. They appear in the geological record precisely where they should, at the boundaries of the cryogenian glaciations, marking the transition from frozen to thawed conditions. For geologists, they are smoking guns, evidence that the ocean really was anoxic and iron-rich during the glaciations. But the ocean during Snowball Earth was not entirely dead. Geothermal heat from the planet's interior continued to warm the water from below. Hydrothermal vents, fissures in the ocean floor where superheated water laden with minerals gushes out, kept operating throughout the glaciation. These vents are powered by volcanic activity, by the slow decay of radioactive elements in the Earth's mantle, and by the heat generated by the planet's own formation. They don't depend on sunlight or surface conditions, they simply persist, as they have for billions of years. Around these vents, life found a foothold. The organisms that lived there were chemotrophs, creatures that derive energy not from light but from chemical reactions. They fed on hydrogen, sulfide, methane, and other compounds released by the vents. These organisms formed the base of a food web that existed entirely independently of the sun, a shadow ecosystem in the darkness of the frozen ocean. Similar ecosystems exist today around deep-sea hydrothermal vents, and they may represent a window into what life was like during Snowball Earth. The tube worms, shrimp, and microbial mats that cluster around modern vents are not the same species that existed 700 million years ago, but they give us a sense of the possibilities. Life in the deep ocean doesn't need sunlight. It doesn't need a warm surface. It needs only energy, in whatever form is available. The circulation of the Snowball Ocean was also unusual. Today, ocean circulation is driven largely by wind and by differences in temperature and salinity between different water masses. Warm water at the equator is heated by the sun, expands and rises. Cold water at the poles cools, contracts and sinks. This creates a global conveyor belt, carrying heat and nutrients around the planet. During Snowball Earth, this circulation was transformed. With the surface covered by ice, there was no wind-driven mixing. The temperature gradient between the equator and the poles was reduced because both were frozen, but the ocean was not stagnant. Geothermal heating from below created convection currents, pushing warm water upward from the ocean floor. These currents mixed the water, preventing complete stratification and keeping the ocean in motion. The details of this circulation are still being worked out by computer models. Some simulations suggest that the Snowball Ocean was surprisingly turbulent, with strong vertical mixing driven by the contrast between cold ice above and warm vents below. Others suggest a more layered structure, with dense, salty brine pools at the bottom and fresher water above. The reality was probably complex, varying from place to place and changing over the millions of years of glaciation. One particularly important feature was the accumulation of salt. When seawater freezes, the salt is left behind. The ice that formed during Snowball Earth was relatively fresh, while the remaining liquid water became increasingly salty. Over millions of years, as more and more water was locked up in ice, the salinity of the ocean may have doubled. This hypersaline water had a lower freezing point, allowing it to remain liquid at temperatures well below zero. It also affected the density and circulation of the water, creating conditions unlike anything in the modern ocean. The hypersaline Snowball Ocean may have reached temperatures as low as -15 degrees Celsius in the coldest brine pools. These were extreme conditions, hostile to most forms of life we know. But some organisms can tolerate high salinity and low temperatures. Certain bacteria and archaea, the most ancient domains of life, are found today in salt lakes and polar brines. Their ancestors may have survived Snowball Earth in similar environments, waiting out the long freeze in pockets of concentrated, frigid water. The question of life survival during Snowball Earth has implications far beyond our own planet. Scientists who study the possibility of life elsewhere in the solar system are deeply interested in how organisms coped with the cryogenian glaciations. The conditions under the ice, dark, cold, cut off from the atmosphere, are remarkably similar to those that might exist beneath the frozen surfaces of moons like Europa and Enceladus. Europa, a moon of Jupiter, has a surface covered entirely in ice, but beneath that ice, heated by tidal forces from Jupiter's immense gravity, there is almost certainly a liquid ocean. This ocean is larger than all of Earth's oceans combined, and it has existed for billions of years. If life can survive in the darkness of a Snowball Earth ocean, might it also survive, or even originate in the darkness beneath Europa's ice? The same question applies to Enceladus, a small moon of Saturn that sprays plumes of water vapor into space from cracks in its icy surface. The source of these plumes is a subsurface ocean, kept liquid by tidal heating. Hydrothermal vents may exist on the floor of this ocean, just as they did during Snowball Earth. If life could cling to existence around vents in a frozen Earth, it might also find purchase in the depths of Enceladus. These are not idle speculations. Space agencies are actively planning missions to explore these ocean worlds. The lessons of Snowball Earth are directly relevant to how we search for life elsewhere. We know that life doesn't need sunlight. We know that it can survive extreme cold and high salinity. We know that hydrothermal vents can sustain ecosystems for millions of years without any input from the surface. All of this gives us reason to hope that the universe may be more hospitable to life than we once thought. Returning to Earth, let us consider the long aftermath of Snowball Earth, the period of recovery and change that followed the melting of the ice. The transition from frozen planet to greenhouse world was one of the most dramatic environmental shifts in Earth's history. As the ice retreated, the planet entered a brief phase of extreme warmth. Carbon dioxide, levels which had built up to hundreds of times their current concentration, created a powerful greenhouse effect. Temperatures soared. The hydrological cycle, dormant for millions of years, roared back to life with a vengeance. Rain fell in torrents on the newly exposed land, washing sediments into the sea and chemically weathering the rocks at unprecedented rates. The chemical weathering that followed the glaciation was extraordinary. Fresh rock surfaces, exposed by the retreating ice, were attacked by acidic rainwater charged with dissolved carbon dioxide. Calcium, magnesium, and other minerals were stripped from the rocks and carried to the ocean. There, they combined with carbon to form carbonate sediments, the thick cap carbonates that now mark the end of each Snowball glaciation. This process drew down atmospheric carbon dioxide, gradually cooling the planet from its post-glacial hothouse state. But the recovery was not smooth. The Earth swung through wild oscillations of temperature and chemistry as it settled into a new equilibrium. The oceans, stratified by the influx of fresh meltwater, took thousands of years to mix fully. The atmosphere, loaded with volcanic gases and weathering products, was chemically unstable. Life, newly released from its frozen refugia, had to adapt rapidly to conditions that were changing almost as fast as it could evolve. The Ediacaran period, which followed the Marinoan glaciation, was a time of experimentation. In the warm, oxygen-rich waters of the post-Snowball ocean, new forms of life appeared. The Ediacaran biota, those strange frond-like and quilted organisms, represented something new in the history of life. Large, multicellular creatures that lived in communities on the seafloor. They were not animals in the modern sense, and their relationship to later life remains debated. But they were complex and they were diverse. For the first time in Earth's history, life was visible to the naked eye. The rise of the Ediacaran biota may have been driven by the same environmental changes that ended Snowball Earth. Higher oxygen levels allowed larger organisms to evolve. The mixing of the ocean brought nutrients to the surface. The extinction of whatever simpler organisms had dominated before opened ecological niches. And the extreme conditions of the glaciation itself may have favoured organisms that could cooperate, communicate and adapt, traits that would become hallmarks of animal life. The Ediacaran period lasted from about 635 million years ago to roughly 539 million years ago. During this time, life experimented with body plans and lifestyles that would not be seen again. Some Ediacaran organisms were so strange that scientists have proposed placing them in their own kingdom, separate from animals, plants, fungi, and protists. They were evolutionary dead ends in a sense, lineages that flourished for a time and then vanished, leaving few, if any, descendants. But the Ediacaran also saw the first stirrings of what would become the animal kingdom. Trace fossils from this period, the burrows and tracks left by moving organisms, show that some creatures were beginning to crawl and dig. These were bilaterians, animals with a distinct front and back, left and right. They were the ancestors of almost every animal alive today, from worms to whales to humans. Their appearance at the tail end of the Ediacaran set the stage for the explosion of diversity that would follow. The Cambrian period, which began around 539 million years ago, is famous for its burst of evolutionary innovation. In a geologically short span of perhaps 20 to 30 million years, most of the major animal groups appeared in the fossil record for the first time. Trilobites crawled on the seafloor. Anomalocaris, a predator the size of a small dog, hunted in the water column. The ancestors of fish, of insects, of mollusks and crustaceans all made their debut. This Cambrian explosion, as it's called, has puzzled scientists for over a century. Why, after billions of years of mostly single-celled life, did complex animals suddenly diversify so dramatically? Many hypotheses have been proposed, from rising oxygen levels to the evolution of eyes to ecological arms races between predators and prey. But one factor that keeps coming up is the legacy of Snowball Earth. The extreme environmental perturbations of the Cryogenian may have cleared the deck, eliminating incumbent organisms and opening space for new ones. The intense selection pressure of surviving a frozen planet may have accelerated evolutionary innovation. The oxygenation of the deep ocean, driven by the mixing and weathering that followed the glaciations, may have finally provided the chemical conditions that large active animals require. Some scientists have even suggested that the Cambrian explosion was, in a sense, a delayed reaction to Snowball Earth, the full flowering of evolutionary potential that had been building during the glaciations, but could only be expressed once conditions stabilized. The connection between Snowball Earth and the Cambrian explosion remains a subject of active research. Not all scientists agree that the link is causal. Correlation is not causation, and the timing, while suggestive, is not proof. But the coincidence is striking. For billions of years, life was simple. Then the planet froze, twice, in the most extreme glaciations in its history. And almost immediately afterward, complex animals appeared and diversified. Whether Snowball Earth caused the Cambrian explosion, contributed to it, or simply preceded it by chance, the two events are forever linked in the geological record. They represent together one of the most important transitions in the history of life on Earth. Before we move on, let us pause to consider what it would have been like to witness the end of Snowball Earth. Imagine, if you can, a world that has been frozen for millions of years. The ice stretches from horizon to horizon, white and silent and seemingly eternal. The sun rises and sets, but its warmth cannot penetrate the thick shell that covers the planet. Beneath the ice, the ocean lies in darkness, its waters cold and strange, its chemistry utterly unlike anything we know. And then, slowly at first, things begin to change. The carbon dioxide that has been accumulating in the atmosphere for eons finally reaches a critical threshold. The greenhouse effect intensifies. The ice, which has seemed so permanent, begins to soften. Cracks appear on the surface, meltwater pools in the hollows, and then, in a rush that must have seemed apocalyptic to any life that witnessed it, the ice begins to retreat. The thaw, when it came, was violent. The ice did not simply melt away in a gentle warming, it collapsed. Glaciers that had covered continents for 50 million years broke apart and slid into the sea. Rivers of meltwater carved canyons through the ice, carrying debris and sediment into the newly exposed ocean. The sea level rose as the ice turned back into water, flooding coastal areas that had been dry land for longer than complex life had existed. The atmosphere, supercharged with carbon dioxide, created a greenhouse effect unlike anything before or since. Temperatures soared, rain fell in torrents, acidified by the dissolved carbon dioxide, attacking the rocks with a fury that left permanent marks in the geological record. The ocean, stratified by the influx of fresh water, turned strange colours as chemical reactions played out in its upper layers. Minerals precipitated out of the water in vast quantities, forming the cap carbonates that now serve as markers of this extraordinary transition. It was, in every sense, a new beginning. The world that emerged from Snowball Earth was not the same world that had frozen over millions of years before. The chemistry had changed, the biology had changed, the very structure of the ocean and atmosphere had been transformed. Life, which had survived in scattered refugia, now found itself in a completely different environment, one with new challenges and new opportunities. The organisms that emerged from Snowball Earth were the ancestors of everything alive today. Every fish and frog, every tree and flower, every insect and mammal, including humans, can trace its lineage back to the survivors of the Cryogenian glaciations. We are all descendants of the organisms that clung to hydrothermal vents, that huddled in meltwater pools, that found ways to persist through 50 million years of ice and darkness. Their resilience is built into our genes. Their adaptations shaped the fundamental biology that all complex life shares. This is worth contemplating. When you look at your own hand, with its bones and muscles and skin, you are looking at a structure that was shaped by billions of years of evolution, including the crucible of Snowball Earth. The cells that make up your body are running metabolic processes that first evolved in organisms that survived the frozen ocean. The oxygen you breathe was produced by photosynthetic organisms that found ways to persist through the glaciations. In a very real sense, you are a product of Snowball Earth, a living testament to the resilience of life on this planet. The scientific study of Snowball Earth has advanced remarkably in recent decades. What was once a controversial hypothesis is now accepted by most geologists and paleontologists as the best explanation for the evidence. But the study is far from complete. New discoveries continue to refine our understanding of when the glaciations occurred, how severe they were, and what conditions allowed life to survive. One active area of research concerns the exact timing and duration of the glaciations. Early estimates place the Sturtian glaciation at roughly 717 to 660 million years ago, a span of about 57 million years. But recent dating techniques, using high-precision uranium lead analysis of volcanic rocks interbedded with glacial deposits, have allowed scientists to narrow these estimates. The current consensus is that the Sturtian glaciation began around 717 million years ago and ended around 660 million years ago. The Marinoan glaciation is dated from roughly 640 to 635 million years ago, a much shorter event. Some researchers have suggested a third, even later glaciation, the Gaskiers glaciation, around 580 million years ago, though this event appears to have been less severe and may not have reached the tropics. Another area of active research concerns the mechanisms that ended the glaciations. While the buildup of volcanic carbon dioxide is widely accepted as the primary driver of the thaw, the details remain uncertain. How much carbon dioxide was needed to overcome the ice albedo feedback? How quickly did it accumulate? What role did other greenhouse gases such as methane play in the process? These questions are being addressed through a combination of geological evidence and computer modelling, but definitive answers remain elusive. The role of life in Snowball Earth is also being actively investigated. For many years, the prevailing view was that life was a passive victim of the glaciations, simply enduring whatever conditions the climate imposed. But recent research has suggested that life may have played an active role in both triggering and ending the ice ages. Before the Sturtian glaciation, for example, photosynthetic organisms may have drawn down atmospheric carbon dioxide, contributing to the cooling that led to the freeze. During the glaciations, methane-producing microbes in the deep ocean may have helped maintain minimal greenhouse conditions, and after the thaw, the rapid diversification of life may have influenced the carbon cycle in ways that affected subsequent climate. These ideas are speculative, and the evidence for them is still being gathered, but they suggest that the relationship between life and climate is more complex and reciprocal than was once thought. Life doesn't just respond to climate, it shapes climate. And understanding this relationship is crucial for understanding both the deep past and the present. The discovery of similar features on other planets and moons has added a new dimension to Snowball Earth research. Mars, for example, shows evidence of ancient water and possibly even ancient ice ages. The polar ice caps of Mars are composed of both water ice and frozen carbon dioxide, and their behavior over Martian history may have included periods of expansion and contraction similar to those on Earth. Whether Mars ever experienced a full snowball state is unknown, but the question is being actively explored by planetary scientists. Europa and Enceladus, as we've discussed, present even more intriguing possibilities. These icy moons may have subsurface oceans that have existed for billions of years, heated by tidal forces rather than sunlight. The conditions in these oceans may be similar to those that existed beneath the ice of Snowball Earth, with hydrothermal vents providing energy and nutrients for whatever life might exist. The discovery of life on Europa or Enceladus would have profound implications for our understanding of Snowball Earth and for the prospects of life elsewhere in the universe. Even exoplanets, worlds orbiting other stars, are now being studied for their potential to experience snowball-like conditions. The habitable zone, the region around a star where liquid water can exist on a planet's surface, is defined in part by the balance between incoming stellar radiation and greenhouse heating. Planets on the outer edge of this zone might be vulnerable to runaway glaciation, especially if their atmospheres are low in greenhouse gases. Understanding how Earth escaped from snowball conditions could help scientists predict whether similar planets might be habitable or locked in permanent freeze. The study of snowball Earth has thus become part of a broader effort to understand planetary habitability. What makes a planet capable of supporting life? How do climate and geology interact to create conditions favourable or hostile to biology? What are the limits beyond which a planet cannot recover from extreme climate events? These questions, which once seemed abstract, have become urgent as we search for life elsewhere in the cosmos, and as we confront the reality of climate change on our own world. Let us turn now to a question that has been lurking in the background throughout our journey. What does snowball Earth mean for our understanding of climate? The cryogenian glaciations are sometimes called the most extreme climate events in Earth's history. They represent the ultimate expression of the ice albedo feedback, runaway cooling that brought the planet to the edge of permanent freeze. Understanding how they started, how they ended, and what conditions they created is not just an exercise in paleontology. It has direct relevance to our understanding of how climate works. The basic physics of snowball Earth is the same physics that governs climate today. Greenhouse gases trap heat, ice reflects sunlight, ocean circulation distributes energy. The carbon cycle moves carbon between reservoirs on timescales ranging from years to millions of years. All of these processes are still operating, and all of them can push the climate in one direction or another depending on circumstances. What snowball Earth teaches us is that the climate system can have multiple stable states. Under certain conditions, the planet tends toward a warm, ice-free equilibrium. Under other conditions, it tends toward a cold, ice-covered equilibrium. And the transition between these states can be abrupt, driven by positive feedbacks that amplify small changes into large ones. This concept of climate tipping points is increasingly relevant to modern discussions of global warming. Scientists have identified a number of potential tipping points in the current climate system, thresholds beyond which change becomes self-reinforcing and difficult to reverse. The melting of the Greenland ice sheet, the thawing of Arctic permafrost, the die-off of the Amazon rainforest. All of these are processes that could accelerate if pushed past certain limits. Snowball Earth is an extreme example of what happens when a tipping point is crossed, but the underlying dynamics are the same. Of course, the modern Earth is not at risk of freezing over. Atmospheric carbon dioxide levels are far higher than they were before the cryogenian glaciations. The sun is brighter. The configuration of the continents is different. By every measure, the planet is much warmer than the threshold that would trigger runaway glaciation. If anything, the current risk is in the opposite direction. Not too little greenhouse effect, but too much. But the lesson of snowball Earth is not about the specific direction of climate change. It's about the capacity of the Earth system to undergo rapid, irreversible transitions. It's about the danger of pushing the climate past thresholds that, once crossed, cannot easily be uncrossed. And it's about the importance of understanding the feedbacks that govern climate, so that we can anticipate their effects before they take us by surprise. Scientists who study snowball Earth are often asked whether it could happen again. The answer, as we've seen, is that a new snowball is extremely unlikely under current conditions. The same feedbacks that would be needed to trigger runaway glaciation are being overwhelmed by the warming effects of greenhouse gases. The ice caps are melting, not growing. The albedo of the planet is decreasing, not increasing. We are moving away from, not toward, a frozen state. But the question itself is valuable because it forces us to think about the limits of the Earth system. How much can the climate change before it tips into a new state? How fast can that change occur, and what would the consequences be for life? These are not abstract questions. They are the central challenges of climate science in the 21st century. Looking far into the future, hundreds of millions of years from now, the question of whether snowball Earth could return becomes more interesting. The Earth's climate is controlled by a complex interplay of factors, including the brightness of the sun, the configuration of the continents, the composition of the atmosphere, and the activity of life itself. Over very long timescales, all of these factors can change. The sun is slowly brightening, which would tend to warm the planet, but volcanic activity could decline, reducing the supply of carbon dioxide to the atmosphere. Continental drift could carry land masses, into configurations that favour weathering and carbon burial. And changes in life itself, whether natural or caused by future intelligence, could alter the carbon cycle in unpredictable ways. Some researchers have speculated about what might happen when the next supercontinent forms, perhaps 200 to 300 million years from now. Current models suggest that this future supercontinent, sometimes called Pangaea Ultima or Amasia, could be extremely hot, with temperatures that might threaten the survival of complex life. But other factors could intervene. If volcanic activity declines as the supercontinent stabilizes, carbon dioxide levels might drop, potentially triggering a new ice age. The interplay between these factors is too complex to predict with confidence, but it's a reminder that the Earth's climate is never truly static. Change is the only constant, whether we're talking about the deep past or the deep future. The study of Snowball Earth has also had practical applications beyond understanding Earth's history. Climate scientists use the cryogenian glaciations as a test case for their models. If a climate model can't reproduce Snowball Earth, it's missing something important about how the climate system works. Conversely, models that successfully simulate the onset and termination of Snowball Earth give us more confidence in their predictions about future climate change. The extreme conditions of the cryogenian push models to their limits, revealing assumptions and approximations that might not matter under more normal conditions. This process of testing models against the distant past has helped improve our understanding of climate feedbacks and has contributed to the development of more robust climate projections. The philosophical implications of Snowball Earth are also worth considering. The frozen planet serves as a reminder of how fragile habitability can be. Life on Earth has persisted for nearly 4 billion years, surviving asteroid impacts, volcanic catastrophes, and at least 2 periods of near-total glaciation. But it has not persisted unchanging. Each crisis has left its mark, shaping the course of evolution and determining which lineages survived and which went extinct. The survivors of Snowball Earth went on to populate the Ediacaran seas and eventually gave rise to the Cambrian explosion. We are their descendants, inheritors of a legacy that includes both the resilience to survive extreme conditions and the adaptations that emerge from those conditions. In a sense, Snowball Earth is part of why we exist. If the glaciations had been slightly different, if life had failed to survive, if the thaw had not occurred when it did, the entire subsequent history of life would have been altered. The animals that evolved in the Cambrian might never have appeared. The path that led from simple marine organisms to fish, to amphibians, to reptiles, to mammals, and eventually to humans might never have been taken. We are products of contingency, of the particular sequence of events that happened to occur on this particular planet over the course of 4 billion years. Snowball Earth is one of those events, a crucial chapter in the story that led to us. And what of the future of life on Earth? The planet has weathered many crises, and life has always found a way through. But the current moment is unusual in several ways. For the first time, a single species, humans, has become a dominant force in the Earth system, capable of altering the climate, the chemistry of the ocean, and the composition of the biosphere on a global scale. We're conducting an experiment with no controls and no do-overs, pushing the planet into territory it hasn't occupied for millions of years. The lessons of Snowball Earth are relevant here too. They remind us that the Earth system has limits, that feedbacks can amplify small changes into large ones, and that transitions, once begun, can be difficult to reverse. They also remind us that life is resilient, that it has survived far worse than anything humans are likely to cause, and that the Earth will continue, with or without us. This is not a reason for complacency, but it is perhaps a reason for humility. We are not the first crisis the planet has faced, and we won't be the last. There remains, even now, genuine scientific debate about the nature of Snowball Earth. Was it truly a hard snowball, with ice covering every inch of the planet's surface? Or was it more of a slush ball, with thin ice or patches of open water in the tropics? The distinction matters because it affects our understanding of how life survived, and how the planet eventually escaped the freeze. The hard snowball hypothesis has the advantage of simplicity. It explains why the ice albedo feedback didn't stop part way. Once ice reached tropical latitudes, the feedback should have continued until the entire surface was frozen. Climate models that include realistic representations of ice physics tend to produce hard snowball states when pushed to cryogenian conditions. The geological evidence too supports extensive ice cover, with glacial deposits found at equatorial latitudes on multiple continents. But the hard snowball hypothesis also has problems. Chief among them is the question of how life survived. A planet completely covered in thick ice, with no light reaching the ocean, would have been extraordinarily hostile to photosynthetic life. Yet the fossil record shows that photosynthetic organisms, including eukaryotes, persisted through the glaciations. This suggests that some light must have penetrated somewhere, either through thin ice near the equator or through cracks and melt pools on the ice surface. The slush pool hypothesis offers an alternative. It suggests that while ice covered most of the planet, the tropics retained some areas of thin ice or open water. These areas would have been kept liquid by ocean currents, by geothermal, heat, or by the simple physics of ice at the freezing point of seawater. They would have allowed light to penetrate, supporting photosynthesis and providing refugia for complex life. The slush pool hypothesis is harder to model precisely because it requires balancing the ice albedo feedback against other factors that resist complete freezing. But it may be more consistent with the biological evidence. Recent climate simulations from NASA's Goddard Institute for Space Studies have provided some support for the slush pool picture. These simulations, which incorporate sophisticated representations of ocean circulation, show that even under very cold conditions, ocean currents can prevent complete freezing near the equator. The models produce stable slush pool states, with extensive ice cover but persistent areas of open water, that are consistent with both the geological and biological evidence. These findings don't settle the debate, but they suggest that the reality may have been somewhere between the hard snowball and the slush ball extremes. The circulation of the ocean beneath the ice is another area of active research. Computer models suggest that the snowball ocean was not stagnant, but was kept in motion by geothermal heating from below and by the temperature gradient between the cold ice above and the warm vents on the ocean floor. This circulation would have mixed nutrients and gases through the water column, potentially creating conditions hospitable to at least some forms of life. The details of this circulation, including its strength, its pattern, and its variability over time, are still being worked out. Different models produce different results, depending on their assumptions about ice thickness, ocean salinity, and geothermal heat flow. But the general picture is one of a dark but dynamic ocean, kept alive by the slow beat of the Earth's internal heat. The evidence for Snowball Earth continues to accumulate. In recent years, researchers have discovered new sites where cryogenian glacial deposits are preserved, from Scotland to Oman to Mongolia. Each new site adds detail to our picture of the glaciations, revealing local variations in ice thickness, ocean chemistry, and the timing of events. Advanced dating techniques have allowed scientists to pinpoint when the glaciations began and ended with increasing precision, and new analytical methods have opened windows into conditions that were previously inaccessible, from the temperature of the ancient ocean to the composition of the atmosphere. One particularly exciting development has been the discovery of biomarkers in cryogenian sediments. These molecular fossils, preserved in rock for over 600 million years, tell us something about the organisms that lived during and after the glaciations. Some biomarkers point to the presence of sponges or their ancestors, suggesting that early animals may have already evolved before the ice ages ended. Others indicate the presence of certain algae or bacteria, helping researchers map out which groups survived the freeze and which did not. Biomarker research is still in its early stages, and interpretations are sometimes contested. But the potential to reconstruct ancient ecosystems at a molecular level is tantalizing, offering glimpses into a world that left few other traces. The cultural impact of Snowball Earth has been significant, extending well beyond scientific circles. The idea of a frozen planet has captured the popular imagination, appearing in documentaries, books, and even science fiction. The visual image of a white Earth, seen from space, is striking and memorable. It conveys, in a single frame, how dramatically our planet can change. For many people, Snowball Earth serves as an entry point into deep time, a way of grasping just how old and how strange our planet's history really is. It's also become a touchstone in discussions about climate change, as an extreme example of what happens when carbon dioxide levels drop too low. Of course, the opposite extreme, a runaway greenhouse, is more relevant to current concerns. But Snowball Earth reminds us that the climate system can move in either direction, given the right conditions, and that the consequences can be profound. The study of Snowball Earth also connects to broader questions about the nature of planets and habitability. In recent decades, astronomers have discovered thousands of exoplanets orbiting other stars, including many in the so-called habitable zone, where liquid water could exist on the surface. But being in the habitable zone is no guarantee of habitability. A planet's climate depends on many factors beyond just its distance from its star, including the composition of its atmosphere, the nature of its surface, and the presence or absence of a magnetic field. Some exoplanets may be locked in permanent snowball states, their surfaces frozen over regardless of how close they are to their star. Others may oscillate between frozen and greenhouse conditions, as Earth has done over its history. Understanding how Earth escaped from snowball conditions and what conditions allowed life to survive is directly relevant to assessing the habitability of these distant worlds. If life can survive a snowball Earth, it may be more common in the universe than we once thought. The frozen planet may be more a phase that planets pass through than a permanent state, and the ability to escape from it may be a key factor in whether a planet can support complex life. There is something deeply humbling about contemplating Snowball Earth. The frozen planet reminds us that the conditions we take for granted, liquid oceans, breathable air, moderate temperatures, are not inevitable. They are the product of a delicate balance, maintained by processes that operate over timescales we can barely comprehend. The Earth has been frozen before, and it thawed. It has been hot before, and it cooled. It has been oxygenated and anoxic, fertile and barren, teeming with life and nearly lifeless. Through it all, the planet has persisted, and life has found a way. This resilience is encouraging, but it should not make us complacent. The Earth will continue, with or without us. The question is what kind of Earth we will leave behind, and what lessons we will have learned from its long and strange history. As we approach the end of our journey, let us step back and consider the broader picture. Snowball Earth is one chapter in a story that spans 4.5 billion years. It is a dramatic chapter, to be sure, one of the most extreme events in the planet's history. But it is not isolated. It is connected to everything that came before and everything that followed. The conditions that triggered the glaciations were set in motion by plate tectonics and the carbon cycle. The life that survived them had been evolving for billions of years before the ice arrived. The complex animals that emerged afterward would go on to colonize land, build ecosystems, and eventually give rise to minds that could look back and wonder about the frozen past. In this sense, Snowball Earth is not just a geological curiosity, it is part of our heritage, woven into the fabric of the living world. The oxygen we breathe, the animals we share the planet with, even the configuration of the continents and the chemistry of the ocean, all bear the imprint of those ancient glaciations. We are products of a history that includes Snowball Earth, even if we don't usually think of it that way. And perhaps that is the deepest lesson of all. The Earth is not a static backdrop against which history unfolds. It is a participant, an active player whose moods and cycles shape the course of life. The frozen world of the Cryogenian was not a punishment or a mistake. It was simply what happened when certain conditions aligned, and life, remarkable life, found a way to survive it, to emerge from it, and to flourish in its aftermath. That resilience is encouraging. It suggests that life is tough, adaptable, capable of enduring conditions that would seem hopeless. It gives us reason to believe that whatever challenges lie ahead, whether from climate change, asteroid impacts, or other catastrophes, life will find a way through. Not unchanged, perhaps, but continuous, carrying forward the spark that has burned since the first cells appeared in ancient seas. Rest now. Let the cold of 700 million years ago settle into your imagination like a dream half remembered. Picture the endless ice, the silent oceans, the faint glow of hydrothermal vents in the darkness. Picture the first thaw, the roar of waterfalls as glaciers melted, the strange new creatures emerging into a world transformed. Think of the banded iron formations, those striped rocks that record the chemistry of a frozen ocean. Think of the cap carbonates, the thick limestone layers that mark the moment the greenhouse took hold. Think of the Ediacaran biota, those quilted and frond-like organisms that represented life's first experiments with complexity. All of this happened on the same planet where you now lie, listening to these words. The atoms in your body were present then, circulating through rocks and water and air. They have been recycled countless times, built into organisms and broken down again, carried by currents and winds across a world that has changed beyond recognition. You are made of snowball Earth, in a very real sense. Its history is written in your chemistry. Consider for a moment the improbability of it all. A planet forms from dust and gas in the chaos of a young solar system. It survives billions of years of bombardment, volcanism, and chemical transformation. Life appears, clings to existence, learns to harvest sunlight, begins to reshape the atmosphere. And then, just as things seem to be settling into a pattern, the climate tips into a new state, one where ice covers everything and the rules change completely. Life survives this too, hiding in cracks and vents and pools, waiting out the long freeze. And when the ice melts, life doesn't just resume where it left off. It explodes into new forms, new possibilities, new ways of being. The Ediacara and Biota emerge, strange and wonderful. The Cambrian explosion follows, populating the seas with creatures that would look familiar even today, trilobites and worms and early chordates. The ancestors of every fish and frog and bird and mammal take their first tentative steps into a world that has been remade by ice and fire. The ice ages of the Cryogenian were not the only extreme events in Earth's history, but they were among the most severe. The only comparable glaciations occurred much earlier, during the Huronian ice ages over 2 billion years ago, when the Earth may also have experienced near-global freezing. These earlier events are less well understood, partly because the rocks that record them are older and more altered, and partly because less research has focused on them. But they share some features with the Cryogenian glaciations, including evidence of ice at low latitudes and abrupt transitions to warmer conditions. Some scientists believe the Huronian glaciations may have been triggered by the Great Oxidation Event, when rising oxygen levels destroyed atmospheric methane, a powerful greenhouse gas. If true, this would mean that life itself caused the first snowball Earth, a sobering reminder of how biology and climate are intertwined. The future, of course, remains unwritten. We cannot know what challenges the Earth will face in the millions and billions of years to come. The sun will continue to brighten, gradually warming the planet until, in about 1 billion years, conditions may become too hot for complex life. Before that happens, countless other events will shape the planet's trajectory, from volcanic eruptions to asteroid impacts to changes in the configuration of the continents. The ice may return, or it may not. The climate will continue to oscillate as it always has between warmer and cooler states, and life will continue to adapt as it always has, finding new niches and new solutions to the challenges it faces. What we can say is that the Earth has a remarkable capacity for recovery. Every crisis in its history, no matter how severe, has been followed by a period of renewal. The great extinctions that punctuate the fossil record were not endings but transitions, clearing the way for new forms of life to emerge. The Snowball Earth events were no exception. From the frozen depths of the Cryogenian came the ancestors of every animal that walks, swims, or flies on the planet today. The ice did not defeat life, it transformed it, and then let it go. The ice has melted, the sun is warm, the present is here, and you are part of it, a living link in the chain that stretches back to those earliest survivors and forward to whatever comes next. The Earth has been frozen before, and it may freeze again, in some unimaginably distant future when conditions once more align. But for now, it turns beneath a star, blue and green and alive, its oceans liquid, its atmosphere breathable, its surface teeming with life that traces its ancestry back through the Cambrian explosion, through the Ediacaran experiments, through the refugia of the frozen ocean, all the way to the first cells that learned to harvest energy from the world around them. You are part of that story. Every breath you take connects you to the organisms that first oxygenated the atmosphere. Every heartbeat echoes the rhythms that life has followed for billions of years. And every night, when you close your eyes and drift towards sleep, you're continuing a tradition as old as consciousness itself. The rest that allows life to continue. The pause that makes tomorrow possible. The question we asked at the beginning, could the oceans freeze again, has an answer now. They could in principle, but they won't. Not on any timescale that matters to us. The conditions are wrong. The sun is too bright. The atmosphere is too thick with greenhouse gases. We're safe from the ice, at least for now. But the forces that shaped Snowball Earth are still at work. The feedbacks are still there, embedded in the physics of ice and sunlight and carbon. And the lesson they teach is one we would do well to remember. The Earth's climate is not fixed. It can change, and change dramatically. It has done so before, and it will do so again. What matters is understanding how and why, and what we can do to live wisely on a planet that has its own rhythms, its own moods, its own long-term plans. Sleep well, traveller. The night is quiet outside and the world is warm. The ice is far away, locked in mountains and polar caps where it belongs. The ocean is open, catching starlight, rolling with tides that have rolled for billions of years. And somewhere in that ocean, in the dark waters of some volcanic vent, organisms are still living by the same rules that sustained life through Snowball Earth, drawing energy from chemicals, building communities in the absence of light, carrying forward the ancient traditions of life in the deep. They don't know about the frozen past. They don't need to. They simply persist, as they always have, as they always will, until the sun itself grows old and the earth changes once more into something we cannot imagine. These creatures, living in darkness and pressure beyond anything we can experience directly, are living links to the cryogenian age. They remind us that life finds a way, even in the most hostile conditions, even when the surface world has abandoned all hope. For now, though, the present is enough. The Ice Age is a memory written in stone. The future is unwritten and full of possibility, and you, breathing softly in the dark, are the latest chapter in a story that began before there were stories, before there were minds to tell. Them, before there was anything but chemistry and time and the slow patient work of becoming. The frozen planet is behind us now, but its echoes remain in every living thing, in every molecule of air, in the very ground beneath our feet. We are all children of Snowball Earth, inheritors of a legacy written in ice and carbon, and the stubborn refusal of life to surrender. The organisms that survived those 57 million years of cold and darkness passed something down to us. Not just genes and metabolisms, but a kind of resilience that is built into the fabric of life itself. Every cell in your body carries echoes of that ancient survival, traces of adaptations that allowed your ancestors to persist when the world itself seemed to have given up on life. The story of Snowball Earth is thus not just a tale of the past, it is part of your own story, woven into the deepest layers of who you are. Rest now. The Earth is turning, the stars are watching, and the long, strange journey of life continues as it always has into whatever comes next.